Hey, this is Stephen Ramsden from Atlanta, Georgia. We're going to talk about the sun today and its effect on aviation safety. I've been asked to do this presentation and I'm honored to do so, and I hope that you enjoy it. I am a air traffic controller in Atlanta, Georgia, and I operate the largest solar astronomy outreach program in the world. As a nonprofit, my wife Natalie and I are very interested in getting science out to the community and to students, especially in middle school, high school, and college levels. What I do is I go to schools 2 or 3 times a week on my days off from air traffic control, and I lecture students on the sun, how it works, how it affects terrestrial technology, and then I let the kids look through my solar telescopes and then take their own images of the sun. It's been a really good thing. It's been going on for about 4 years now, and it's named after my friend Charlie Bates, who passed away, and it's named in memoriam. So I hope that you enjoy the presentation. And if it's a little bit bumpy or I forget what to say every now and then, I apologize, but I'm just an old Southerner. I'm doing the best I can with it. So today we're going to talk about the formation of the sun. How does the sun work? What is solar wind? What are the hazards to aviation? I have a little inside knowledge on that, having been an air traffic controller for 23 years now. I've seen a lot of weird things happen. And then we're going to talk about the Charlie Bates Solar Astronomy Project. And when I look over here, I'm seeing it broadcast on my screen, so I'm not being distracted. I'm just looking at the larger image because my eyes are not as good as they used to be. So here we go. The sun and all stars were formed originally by nebulas in space. And this is sort of basic, but we're going to go over it anyway. Solar system formation for our particular star is said to have occurred about 4.5 billion years ago. There was a gaseous cloud that contained all atoms and molecules that are in existence today on the Earth and all the planets. They were just floating around in space several light years across. Some type of gravimetric distortion or nearby supernova or some incident triggered a spinning and a compression of this cloud. The cloud compressed and compressed over millions and millions of years until at the core of it, the temperature increased to a point where hydrogen began to fuse into helium. We've heard this story before, but I tell you, every time I look at it, every time I think about it, it's just absolutely amazing to me. And I really love to watch this video provided by the NASA Science Visualization Studio that shows a star forming out of a nebulous compression cloud. It just does something to me, and I hope that you guys see the fantastic nature of this. This is really a step ahead in our theoretical explanation of the solar system. As you can see, some of the planets are starting to form around the star. And interestingly, most of these type compression cloud formations result in binary or trinary stars. We just happen to have been fortunate, I guess, that we had a single star formed. And then all the planets coalesced around it and became the solar system that we know and love today, which fortunately was hospitable to human life. And here we are as sentient, conscious beings able to describe this. Sorry, I love that part. The solar system as we know it, and some people don't like Pluto anymore or whatever. I'm not really interested in that whole debate. We know of it as a planet. It's a planet to me. Obviously, we've got 9 planets, 8 if you ask the British Astronomical Society. Either way is fine with me. We've been stable now, though, for about 4 billion years. This has allowed life to evolve. Luckily for us, it's also allowed technology to progress to the point where there's a need for someone to sit in an air traffic control center and guide planes around the sky through our troposphere. And really, look from the outside looking in, that is also just a remarkable niche in human life that has allowed me to have gainful, lifelong employment. And I'm very fortunate. We all know about Saturn and Jupiter and Uranus, Neptune. There's some extra members in this diagram series and 2003 UB313. Anyway, they're all planets to me. I love them all. This is the way the solar system has evolved now to this point, though. And that's what it looks like, sort of. These are somewhat to scale, but I doubt they're exactly to scale. The sun basically is a hydrogen fusion machine. The sun is a mass of mostly hydrogen gas. It's compressing at the core to a point of around 26 million degrees where hydrogen fusion occurs. But it's not like, two atoms slam together and there you got some helium. It goes through a fairly complicated process. It makes it more fun and challenging to teach it at college level courses as well. There's a little system called the proton-proton cycle, and it's explained here in this diagram where 6 protons basically come together through pressure, temperature, form 1 helium atom and a couple extra protons, and in that process they release energy, and that's what powers the sun. The Einstein's equation E equals mc squared describes how much energy is taken from that tiny amount of mass in the proton-proton cycle that's converted directly to energy. We see it in electromagnetic radiation from the sun, most of it in the visible light spectrum, and coincidentally that's why our eyes have evolved on this planet to be sensitive to those particular visible light wavelengths, because that's what our sun puts out. So had we been born around a planet going around Betelgeuse or some other star, we would have evolved a different sensitivity to light waves based on what that star is putting out. So in effect, we kind of carry a fingerprint of the sun in our eyeballs. And I find that fascinating as well. The energy created by the proton-proton cycle radiates from the core of the sun through the convective zone, the transition zone, up to the surface, which we know is the photosphere. Of course, that's not really a surface, it's a gaseous body. But the photosphere is what we generally refer to as the surface. And photosphere means sphere of light. That's where we generally say the light is emitted from the sun in the solar wind. Part of the solar wind is visible wavelengths of light. Part of it is ionized hydrogen, protons, electrons, etc. The solar wind is released from the sun at the photosphere. Now, of course, we like to study the chromosphere with our hydrogen alpha and calcium K telescopes, and white light telescopes. We like to study the photosphere. But basically, the sun operates as a hydrogen fusion machine. Unfortunately, we don't have a hydrogen fusion machine on this planet yet. We haven't figured out the technology. We're still stuck in the hydrogen fission, or uranium fission, basically, which is really a destructive weapon right now rather than a power source. Hopefully we'll progress beyond this so that we can figure out a way to use hydrogen fusion to create energy and not to kill each other. The solar wind, well, the solar wind, as you can see in this video, is being released at the photosphere. It's charged particles and plasma, primarily ionized electrons and protons, flowing outward from the sun at speeds as high as 900 kilometers per second. Temperatures of up to 1,000,000 degrees Celsius. It's pretty hot. The Earth, the poor little tiny Earth here, seen surrounded by its magnetic field, blocks the majority of the solar wind so that we're still alive and talking about it today, luckily for us. As you can see, the sunlit side of the Earth is buffeted constantly by this solar wind. Goes around the other side of the magnetic field, some of the lines reconnect, etc. We'll talk about that later. But it produces these beautiful auroras at the thinnest part of the magnetic field, at the north and south poles, the northern lights that all of us like to take pictures of. The solar wind is constantly coming from the sun. During different cycles of solar activity, the solar wind will have pulses of strong flares interjected into it, which will increase and decrease the speed of the solar wind, making it more variable. And the speeds of 900 kilometers per second are extremely high. It's generally around 300 to 350 kilometers per second for the solar wind. But that's the thing with solar maximum. We don't know exactly how far it can go. We haven't really been studying the sun long enough to make any reliable predictions on it. There you can see the lines reconnecting, coming back around and causing stronger auroras. My friends in Norway are probably looking at these right now. Unfortunately, here in Atlanta, Georgia, we don't get very many auroras. That's the solar wind. Solar hazards. One of the basics of it are we're pretty close to the sun. We're 93 million miles away, or 8.5 light minutes. We're subjected to various emissions that are collectively considered as space weather. And spaceweather.com, by the way, is a great site to go to and see what's going on with space weather today. Dr. Phillips does a great job there. The continuous portions of the solar wind are solar luminescence, of course, which allows us to see each other and see things on Earth. When I'm at schools, I tell the kids, we're outside in the daytime looking around. There's no light bulbs around here. Something's illuminating everything. It's the sun, even though we're 93 million miles away, so it's pretty bright. Continuous solar wind, of